Looking at 5D, we're going to be looking at two things: trivial sequences and something called long-term steady state. Here are some examples of some trivial sequences, and by trivial we mean pointless. The first one, you'll see that the first term is 8 and each subsequent term plus 0 each time, so we're going to be just producing a sequence of 8s, rather pointless. And the second one, doesn't matter what we start with, we're going to be multiplying by -1, so the next term will be -17 and the next one will be 17, -17 and so on. Also pointless. The third one, not so obviously pointless until you look at it closely. We're starting at 1000, again it doesn't matter where, but you're multiplying by 1.1 and then subtracting 100. Now 1.1 multiplier means we're adding 10%. 10% of 1000 is 100. So in effect we're going to be adding 100 and then subtracting 100. That's not altogether pointless, as you will see in the next example. This one would be useful if you want to keep a population steady. Now someone who's running the fish farm, like we looked at in 5C, they would want to keep the population of fish pretty steady, so they want to know how many to subtract given how many are being born. So here we have a population of 8,000 to start with. We are multiplying by 1.12, so that's how many they're growing by. How many do we subtract to maintaining at 8,000? To work that out, one way would be to say that D needs to be 12% of 8,000. So if you work out that 12% of 8,000 is 960, if you subtract 960 after multiplying by 1.12, then you're going to stick at 8,000 each time. So that's not useless, but it's trivial. Now, finally we come to something called long-term steady state, which is a combination of arithmetic growth and geometric decay. For example, we have a population starting with 10 here. We're going to be multiplying the value by 0.5 and then adding 2. So that is arithmetic growth and geometric decay, all right. What happens when you keep generating this sequence? We're going to be finding something called limit, as you will see shortly. Put that into the calculator. 0.5 times un minus 1 plus 2, starting with 10. That's the table as it appears for the first 10 values. You can see it's going down quite sharply, and then it seems to slow down its decay. If you want to see what the graph looks like, quite interesting, put n equals 1 to 10, x is 1 to 10, and also y equals 1 to 10. That should cover it. And you're going to get a graph like that. Now it looks like the graph is certainly flattening out. It hasn't actually flattened out altogether, but perhaps it will if we look a bit further. Let's have a look. If you go down to the 19th value and the 18th, you can see they're both 4, so it looks like it's flattened out to 4, and that is effectively the limit of this sequence, and we found that by looking at the table, which of course you don't have to do. We'll give you a quicker way of finding out the limit of such a sequence, and it's this formula here. Usually the first one is the easiest one. First of all, remember that r must be between 0 and 1, which is geometric decay. And the limit is going to be d, the difference that you're adding, divided by 1 minus r. The other formula is there if you want to use little r for some reason, but there's not much point in doing that usually. Let's apply that to this problem here. The gardener notices that 4% of her plants are being eaten by wild rabbits, and she plants 6 new ones every week. How many will she have in the long run if she has that? She's got geometric decay and she's got arithmetic growth. Well, 4% is 0.04, and that's coming off each time, so that will give us r is 0.96. D is 6, and you can plug those numbers into the formula. Limit is 6 over 1 minus 0.96, which is 150. And the other stuff there is the other formula giving us the same result. So she will, in the circumstance described in part A, finish up with a regular number of plants 150. But supposing she only wants 100 plants in the garden, well, we can work that out as well by plugging what we know into the formula. In this case, we know that she wants 100, so 100 is the limit. 100 is going to be D, we don't know, divided by 1 minus 0.96 as before. And if you multiply 100 by 1 minus 0.96, you will get the answer 4. So she has to plant 4 new plants each week, and she will therefore get 100 plants in the garden in the long run. So there you are, exercise 5D, all questions starting on page 180. And by the way, we do not do exercise 5E.